Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. It's my pleasure to introduce Kaushik Sen. Kaushik is getting his PhD at Urbana-Champaign, working with Professor Gulaga. Kaushik has done a lot of work in a lot of different areas, but I think he's primarily a program analysis guy. He's done static analysis, dynamic analysis, testing, a bunch of other stuff. And he'll tell you more about it in his talk. He's also recently won a Distinguished Paper Award at FSC 05 for his work on Concolic Testing.
Yeah.
And so anyway, I'll not take any of Kaushik's time, and go ahead.
Thank you, Tishu. So, good morning everyone. Today I'm going to talk about my research, primarily focusing on my work on scalable automated methods for software reliability. So let me first give you an outline of my talk. I'll start by briefly mentioning the motivation behind my research, and after that I'll pick one specific topic of my research, which is dynamic program analysis, and I'll show its applicability to testing concurrent and sequential programs, and then I'll show you some case studies which will show the application of my work to real-world programs, and after that I'll give you the big picture, my research in other areas, and mention some future research plans. Okay, so good. So why is software reliability important? Software is everywhere. It's pervading every aspect of our life, and it's getting more and more complex day by day. And software reliability is a grand challenge nowadays. In fact, in 2002 NIST report claims that software failures currently cost the US economy an estimated $60 billion per year. And if we can improve the software testing infrastructure, then we can save 1/3 of this cost. And it is not the case that we are not trying to develop a reliable software. In fact, in the software industry, 50 to 80% of the total software development cost goes into testing only. So the developers and the industry is trying hard to develop reliable software, but our methods and techniques are not good enough. Now, there are several approaches to address this problem of software reliability, like type systems and safe programming languages, static program analysis, dynamic program analysis, which includes testing and runtime monitoring, model checking and theorem proving and other formal methods, model-based software development and analysis. But each one has its limitation. For example, in case of static analysis, you get false positives. In case of testing, it's mostly ad hoc, where you manually translate the specification into test inputs and you do the testing. In my research, I focused on this domain, which involves dynamic program analysis. It includes runtime monitoring, testing, model checking, and so on. And today in my talk, I'll only focus on testing. I'll give you the technical details of my work in Concolic Testing, and I'll discuss my work in other areas of dynamic program analysis briefly after the technical part. Okay, so next I'm going to describe a new method of testing for sequential programs, which we call Concolic Testing. So what is the motivation behind testing? What is our goal? In testing sequential programs, we want to generate a set of test inputs so that whenever we execute the program on these inputs, we can catch bugs. So for now, I'll only focus on generic bugs, like assertion violations, uncaught exceptions, data rest, deadlock, etc. Later, I'll also talk about specification-related bugs. Now, observe one thing. If we can generate a set of test inputs that would force a program to execute any reachable statement in the program, then we can catch any generic error, like assertion violation or uncaught exception or something like that. Clearly, you can do this if we can execute all the feasible execution paths of a program. Now, let me illustrate, clarify this. Given a sequential program, we can see all the feasible execution paths of the program as this binary tree, which we call the computation tree, where each internal node represents the execution of a conditional statement or an if-then-else statement. And each edge represents the execution of a sequence of non-conditional statements. Now, note one thing. Given a sequential program, there can be several inputs that would force the program along the same execution path. our goal would be to generate a set of inputs so that each path in this tree is executed exactly once. Obviously, we cannot even try to explore the whole tree if it is infinite in size. So in such situations, we restrict our exploration to a finite depth. Or we can use various heuristics like statistical techniques or machine learning or similar static analysis to prune the search space. So let me explain this computation tree through an example, which I'll use as a running example. So consider this function test_me, which is the function we want to test. And it has two inputs, x and y, each of type integer. And there you have an assignment z is equal to double of y, where the function double is defined here. And then you have two conditions. If z is equal to x, then if x is greater than y plus 10, then there is an error. Now, all the feasible execution paths of this program for all possible values of x and y can be seen as this computation tree, which has exactly 3 execution paths. Now, our goal would be to explore this tree. Now, there are several existing approaches to address this problem, and one such method is random testing. In random testing, you generate random values for this x and y, and for these inputs, and then you execute the program. Now, random testing is widely successful in catching many bugs, but it has its limitation. It cannot guarantee good coverage of the program. For example, if we take this simple program test_me, which takes as an input x, and which does this comparison, then if we generate random values for this x, then the probability of hitting this error is extremely low. It's in fact 1 by 2 to the power 32. And the problem becomes even worse if we have inputs which are complex data structures. Then we cannot even try to generate a random input value that will crash the program or that will explode the whole computation tree. So one way to address this problem is to use symbolic testing. In symbolic testing, instead of using random values for the inputs, we use symbolic values for the inputs, and then we execute the program symbolically. And whenever we reach some conditional statement, we try to check whether either of the branches can be taken using a theorem prover. Now, symbolic testing gives us good coverage. Unfortunately, it cannot handle all the features of the real-world program. For example, let us consider this method test_me, which takes as an input x, and which has this conditional x modulo 10 times 4 is not equal to 17. Then there is error 1, and otherwise there is error 2. So here error 2 is only reachable, error 1 is not reachable. Now, if we assume that our theorem prover that is used for the symbolic testing cannot reason about the theory of arithmetic with the modulo operator, which is the case, then at this point a symbolic tester will get stuck. It doesn't know whether either the branches can be reached or not. So it will either stop at this point, or if it is a practical symbolic testing tool, then it will say both the branches are reachable. In that case, it will give false positive. The problem becomes worse if we have some function for which we don't have the code even, like some library function. Then we cannot even think of executing this function symbolically. And then also we cannot decide whether either of the branches can be taken or not. So again, we'll get either false positive or get stuck. Now, to address this problem, we propose to combine random testing and symbolic testing so that we can get the best of both the worlds. And we call this concolic testing. So concolic testing, the word concolic uses this CONC from concrete and olic from symbolic. I picked this name because it doesn't show up in the Google. So it's a controversial name. So I have to mention that I started this work while I was doing my internship at Bell Labs 2 years ago, and then after that I extended it with pointers and data structures, concurrency and distributed message passing and other things. So I'm going to describe this method through a simple example, through the running example. So we want to test this method test_me, which takes input x and y. Now if we generate random values for this x and y, the probability of hitting this error is extremely low. It's 1 by 2 to the power 33. What we propose is to perform the concrete execution and symbolic execution simultaneously. So for that, we create two kinds of state. One is the symbolic state of the program, which is represented by this one, where we initialize the inputs with symbolic values or symbols, At the same time, we also create a concrete state, or the real state of the program, where we initialize the inputs with random values. For example, in this case, x is equal to 22 and y equal to 7. And this line represents the concrete execution, and this line represents the symbolic execution, and this represents the program counter. Now, we execute the program both concretely and symbolically simultaneously. So after the execution of this statement, z becomes 14, which is twice the y, but in the symbolic state, it is 2 times y naught. So it is represented symbolically. And whenever we execute some conditional statement, we generate some condition, which we call the path condition. Now note one thing. Any assignment to the inputs which satisfies this condition would force the program along the same path. Our goal would be to generate another set of inputs so that we can direct the program along a different path. So for that, what we should do? We pick this constraint, we negate it, and we solve it to generate new input values, which is x equal to 2 and y equal to 1. And now when we execute the program, we actually take a different path. And again, we execute the program both concretely and symbolically. And now we go into the then statement, then branch of this conditional. And at the end of the execution, we have this path condition. And we repeat the process. We pick one of the constraint, which is this one. We negate it, and we solve the resultant constraint to get x equal to 30 and y equal to 15. Now, if we execute the program on this newly generated input, then we actually hit the error. Yes?
So earlier you mentioned that reasoning about symbolic constraints is not so easy, and therefore symbolic testing is not as effective.
Yes.
So now, how do we solve such complicated symbolic constraints?
I'll get back to that question. That is exactly the point. And my next few slides, well, not next few, but future some slides will show that. Yes?
Is my understanding right that random values you only generate initially and after?
Yes. Initially, so what we do, we have this computation tree. We generate some random value and execute some path in the program initially. And after that, we pick some node, which is using the depth first search strategy for now. We negate it and solve it to generate a new input. And you try to explore the tree. Now, it may happen that you may have explored the whole tree, and you may have made some approximation, because of which you may have lose your completeness. Then you start it again. Whenever you lose completeness, you generate another fresh set of random values and start the process again. So these two things are interleaved. And also during solving the constraints, you can generate values, new inputs, which are random. So
this solves the problem that actually you might not be able with the solver to find a solution to the negated path condition.
yes.
And you start over.
Over random thing, and then we may be able, like take a simple program. If x cube is greater than 0, then some error. Now if we generate, say, x is equal to minus 10, we may not hit the error, and we stop, because we cannot solve whether a solution for x cube greater than 0. Then if we generate another random value, say x is equal to 10, then we actually hit the error. So here the random testing helps, not the symbolic part. Okay, so we perform this path exploration, and because of this, we call this explicit path model checking, not state model checking. We are trying to explore all the distinct paths in a program. And we continue this process. So you may wonder, so Sumit raised this question, how is it looks like a symbolic testing, how is it helping us? So to illustrate that, let me change this function a little bit. Let z is equal to foo of y, where foo is defined here, which returns a complex expression, v times v modulo 50. Now we perform this concolic execution. Now at the end of the execution, we have this constraint, which is y times y modulo 50 is not equal to x. Now you have to solve this, and we don't know. Our constraint solver cannot handle the modulo operator. So the question is, are we stuck? The same situation can arise if we don't have the function foo at all. We don't have the body of the function. And then we have this constraint, which is foo of y is not equal to x, and we have to solve this. Again, we don't know what foo is supposed to do, so are we stuck? The answer is, since our concrete state is a special case of the symbolic state, we can replace some of the symbolic values by the concrete values, as a result, we do approximation. We are sound, but we lose completeness. We cannot catch all bugs. And if we do so, we get the constraint which is 49 is equal to x. And if we solve it, we get x equal to 49 and y equal to 7. And if we execute the program on this newly generated input, we actually hit the error. So in this way, we can go deep inside the tree. We can skip some of the branches. We may not generate values for those things, but we can gain scalability in this way. So in a way, this concolic testing can be seen as a middle path between random testing and symbolic testing, where we get good coverage like symbolic testing. We can handle complex programs like random testing. We get high coverage. We don't have false positive. And we are somewhat efficient. Okay. So I explained this concolic testing, the key idea behind concolic testing using a very simple example so that it is accessible to a broader audience. But things get complicated when we have pointers and data structures, when we have concurrency and message passing and those kind of things. I'll not go into the details how we handle pointers and data structures, but I'll give you an overview how we handle those things. I'll mention how we handle concurrency though. So in case of pointers, if our input is a pointer, then it can actually point to a memory graph or a complex data structure. And we propose the use of logical input map to represent such data structures symbolically. So for example, this pointer, this data structure is represented by this memory map. So I'll not go into the details. We can discuss this offline. And to track the constraints related to the pointers, we use equality and disequality constraints, which are of this form. P is not equal to null or P equal to null, or P is not equal to some other pointer or it's equal to some other pointer. And at the time of solving the constraints, we do some approximation. We decouple the pointer constraints from the arithmetic constraints. We do approximation. And then we generate equivalence class for each pointer. And then we solve these pointer constraints by either adding a node and pointing it to this P, or deleting a node that is pointed by P, or the equivalence class of P, or make two equivalence class equal by making them point to the same node, or we add a node and point both P or Q to point to that node so that they become unequal. So this is a very brief overview. I'll not go into the details. And we also observe that in the case of constraint solving, we only negate one constraint at a time. So in many cases, our solution should be similar to the previous solution. And we exploit this fact and we implemented an incremental constraint solver, and it turns out that it's 100 to 1,000 times faster than a naive constraint solver. Now, you may ask, like, we are just interested in statement reachability. How this can be used to find like safety and security bugs in programs? The answer is you can always translate this kind of state properties into path properties by automatically inserting checks in the program. For example, suppose I is an input, and if you want to check whether there is a division by 0, then you can insert this thing. If I is not equal to 0, then it's okay, otherwise there is an error. Similar thing happens when you have an array access. Before the array access, you can check whether the input value falls within the range of the buffer length, otherwise it's an error. Similarly, for integer overflow, you can put some checks. So basically, using this automatic instrumentation, you can add these checks and then you can perform concolic testing. Yes?
I might have missed what input languages, what source languages do you apply your techniques to?
We implemented this thing in C and Java for testing C programs and Java programs, but we assume that our core language can be expressed in the RAM model, where we have load and store and conditionals or branching statements.
I guess I'm just wondering on the middle one there. If it's in C, then how do you know what the length of the...
That's a good question. So this is good for Java.
Okay.
In case of C, you have to actually track. Whenever you have allocated some memory location or an array, then you have to keep a track of that and you can add this test. So it can be done at runtime by adding some extra variables. And we don't do this, actually. This is performed by some other tool. We can use it as it is. Yes?
Okay, maybe that answers that. Is there a fundamental reason why you write it as if statements and then some error as opposed to just putting an assertion?
You can do it. Assertions always get compiled to. I just wanted to make it explicit so that you can see that there is a path of branching at this point. You can insert assert as well. That will serve the
Which may not
purpose.
be a path change at all, right? This introduces more paths, whereas an assert does not.
Assert actually introduces a path. If you expand the macro, it checks whether the assertion condition holds or not. Otherwise, it will throw an error. Otherwise, it will go inside the. Yes, yes. So this is a more general thing, I would say. So that's why So instead of error, you can just put assert 0 or something like that. Well, it's not a conditional, you know. Yeah. So I described this concolic testing for sequential programs, but unfortunately, most of the programs in the real world are concurrent programs, where you have several threads or processes executing simultaneously and communicating either through shared memory or through message passing. Now, you can model the execution of such concurrent programs using a scheduler which at every point of execution picks one thread and executes it. Now, the question is, how can we extend this simple method of concolic testing to test concurrent programs? Yes?
So what about multi-threading under multiprocessor configurations?
So in my talk today, I'll only talk about multi-thread programs with shared memory. We have done a separate work for message passing programs where you have separate processes and they communicate through channels or something else. And it's not difficult to combine the things. You have to basically track the points of non-determinism and resolve them in an effective way. That's the thing you have to do. And conceptually, it's not difficult. And this can be extended. So we can actually talk about this. If you're interested, we can talk about it offline. But let's see how it works. Now, testing concurrent programs is notoriously difficult because for a given input, you can have several behaviors of the program depending on how the scheduler resolves the non-determinism. So if you have to test a concurrent program effectively, you have to consider all possible schedules for all possible inputs. And that is going to be a very difficult task. For example, if you consider this two-threaded program, okay, T1, which executes x equal to 100, then a equal to 1, else a equal to 2, and this thread T2 executes another conditional statement. And if we assume that x and y are input to the program, then the computation tree for this simple two-threaded program is this huge tree, where we have nodes not only for the conditional statements, but we also have nodes for the scheduler choice or the thread switch. Now in contrast, if you just consider a single thread, this one, you just forget about this thread, then its computation tree is this one, which has only one node, one internal node. So you get an exponential blow up when you move to concurrent programming. There are several existing approaches to address this problem of testing concurrent programs, and one such method is partial order reduction. So there they observe that a number of executions of concurrent programs are equivalent to each other with respect to statement reachability, and this is called partial order reduction. And then for a given program, they assume that the input space is small or very small, like if it is an integer, it can assume say 0, 1, 2, and 3. Then for each input, they try to test the program using partial order reduction. So these things do not scale for programs which have complex inputs, and at the same time they have concurrency. Now, one way to address this problem would be to combine symbolic testing with partial order reduction. And that is done in the Java Pathfinder tool from NASA Ames, which is a model checker for Java programs. But it has its limitations. It has the limitation of symbolic execution, as I described before. But at the same time, for the purpose of partial order reduction, they have to determine the partial order or the dependency among the various concurrent events. And for that, they have to do pointer analysis and alias analysis so that they can determine whether two pointers are equal and whether they are dependent or not. Now, pointer analysis in case of symbolic execution is always conservative, so it may give rise to a number of redundant dependencies. And as a result, one will explore a lot of redundant executions in the program. So there are serious scalability issues when we combine symbolic execution with partial order reduction. We observed that concolic testing or concolic execution is ideal for testing concurrent programs. Why? We can use the symbolic execution to generate inputs as before, but we have this concrete part, and we can use it to determine the dependency relation exactly. We don't have to do any alias analysis or pointer analysis. So we extended concolic testing with res detection and res flipping, and I'll give you the key steps behind this method next. So executions in concurrent programs can be seen as partial orders, where the partial orders are over events. So in a concurrent execution, events are basically accesses to memory locations. It can be a read or a write or memory acquire or release, lock acquire or lock release. And we say that two events, E and E prime, are related by this partial order reduction if they are events from the different threads, and if they access the same memory location without synchronization, and at least one of them is write, or one of them is lock release and other is lock acquire. Or if they are events on the same thread and one happens before the other, and we take the transitive closure of this relation. Now note one thing, rest conditions are captured exactly by this partial order relation. So let me, and we also made this observation that if we can execute one linear order or one execution for a partial order, then we can reach any reachable statement in the program. We don't have to explore all the linear orders for a partial order. So here is an example of such a partial order. Consider this two-threaded program. T1 executes y equal to 1, x equal to 1, and T2 executes x equal to 3, and if x is not equal to 3, then there is an error. Now let us consider this particular execution, where we first execute T1 and then we execute T2, and this is the partial order corresponding to this execution, where you see that there is a dependency relation between this event and this event, because both of them are accessing the same memory location x without any synchronization. Now, we have this execution. What we should do to get a different partial order? We try to flip this res between these two events. How we can do that? We continue the execution as before for the first event, get the same prefix. Now at this point, we want to flip the res. So for that, what we do, we postpone the execution of the first thread and we continue the other threads to execute. Here we execute thread T2 and then we continue with the remaining of the execution. As a result, this res condition gets flipped and we continue the execution, and actually we hit the error, and as a result we get a new partial order which is slightly different from the previous partial order. And now there are technical things like you have to track these res conditions, you have to make sure that you do not flip these res conditions over and over again repeatedly. So there are certain technical issues which we resolve by using postponement set and delayed sets and slip sets. And then we prove that for this algorithm, this res flipping algorithm explores one linear order for each partial order, or one execution from each equivalence class. And for the purpose of detecting res, we use one of our previous algorithms which we call dynamic vector clock algorithm. This algorithm, yes?
So is the flipping algorithm the same as a dynamic partial order reduction algorithm?
Yeah. So it has some similarities. They actually use, they don't see it as flipping of res. They detect these res conditions or these dependencies, and then they construct these persistent sets, which is different from what we consider. We consider delayed sets. And there are some, and this delayed states was actually proposed in one of the previous work from MIT, and there they didn't consider the dependency, only the dependency among the lock release and lock acquire. So we used that, and we found that this is conceptually more easy to follow, and in some cases actually it works better. So we have some case studies. Moreover, in that work, they consider like any access to a memory location are dependent if they are done by different threads. We say that two reads are not dependent, and that's why we use this dynamic vector clock algorithm. And this was not there in the literature. Algorithms were developed where they just assume that any access to a memory location is dependent if they are accessed by different threads.
Where your algorithm will behave differently from the partial order reduction algorithm.
We have some examples. I can take it offline. Yes.
Your lemma about that one linear execution reaches each statement, that's not the case for all programs. That's why it's a lemma, or is that always true? Or which depends the truth of this lemma? Which condition?
On which conditions?
Yeah. Or is that true for every program?
Well, if you combine with concolic testing, then you do all these approximations. Then you cannot guarantee that you have explored one linear order for each partial order, because of this approximations you may lose some of the partial orders. You may not be able to generate input. So that's why, yeah. And then we can prove some theorem. Actually, I'll get to that later. So in the dynamic vector clock algorithm, we respect the fact that two reads can be permuted. They are not dependent with each other. And then we prove that if two events are related by this race relation, then the vector clock of one event is component-wise less than or equal to the vector clock of the other event. And it's worth mentioning that we took this lemma as our goal, and we derived the whole algorithm mathematically. Now, if we combine this concolic testing with this race detection and race flipping, we end up exploring this small part of the tree. And finally, we prove this theorem, which says that, which gives the soundness and the completeness of this combined algorithm. It says that our algorithm is sound because whenever we find a bug, we have an evidence, an input and a schedule that will lead to that bug. It's not complete in all cases. That is, we cannot guarantee that whatever, we can hit any reachable statement in the program, but we can guarantee the completeness in limited cases. That is, whenever our program terminates and when we do not make any approximation or we can solve any constraint that we have generated, then we guarantee that we have hit any reachable statement in the program.
Question?
Yes.
So then I assume that doesn't happen often.
That doesn't happen often, but means what?
That the constraint solver always solves all the constraints and the algorithm terminates.
Actually, it solves most of the cases if we have like simple programs which are not numerical algorithms or something in graphics. Then the constraints we have observed that they are not complicated. They are mostly linear or simple, and we can solve them. So you don't do approximation that frequently when you have programs using simple data structures or something like that.
But even one kills you, right?
What?
Even one approximation kind of ruins the result.
It ruins the result. We cannot guarantee. But then we can tell the user that we have made some approximations, and this part we may not be able to explore, so you can go ahead and check manually.
So another question. So how do you implemented this race flipping? I mean, do you modify the scheduler? Or?
Yes, we modified the schedule. We implemented it for Java, and there we perform instrumentation. Like before any memory access, we put one function call, which basically gives the control to a central scheduler, which we have implemented, and then it schedules the threads. Now, so far I discussed a new method of testing for concurrent programs and sequential programs, where we can catch generic bugs such as data race, deadlock, assertion violations, and so on. Unfortunately, errors in programs are not only generic, but they can be due to some specification or requirement. So there can be a formal specification of the program for the correctness of the program. So I'll not go into the controversy whether we should have a specification or not, whether it is correct or complete. I'll just assume that we have some specification, and then from that point we want to test it. Now our method for the method that I described is not good when we want to test a program against a formal specification. So let me illustrate that through an example. If we have this two-thread program where x is equal to 3 and y equal to 2, they are executed by different threads. Our method that I described earlier, it will only explore this particular partial order, and it will stop because that's the only partial order in this program. Now we are fine because we have reached all the reachable statements in the program. Unfortunately, if we have a formal specification in temporal logic, say always x is greater than y, then this is not sufficient, because for this partial order we can have another linear order which actually violates this property. At this point x is equal to 0 and y equal to 2, and it violates this condition which is always x is greater than y. So our method is not complete when we have a formal temporal specification. So the question is, do we have to explore the whole tree? Like, do we have to explore all the feasible execution paths of the program for all possible inputs and schedules? The answer is, unfortunately, yes, we have to do it if we have a formal specification. But there is good news. We showed that we can effectively explore all the linear orders for a partial order without re-execution. And this method is called predictive analysis. This we developed, yes?
Why can't you consider the temporal formula just as a further thread or agent which is running beside these two agents, reading x and y, and then it would create some dependencies for the partial order reduction?
Yes, so that's a very good point you noted. Like for this case, you can just have a third thread which can at every access check whether x is greater than y. But if you put such check, how many times you have to execute the program? Actually, you have to execute the program 3 times.
Yeah, for that particular formula, you would then have to consider all interleavings.
And you have to execute, you have to generate schedule for each thing, and you have to consider. But our claim is that we can do it without re-execution. We can just instrument something, get some information, and we can do it. And this is what we call predictive analysis. So I'll describe it. So let me give you the intuitive idea behind this thing. Suppose a cyclist is trying to cross the road because the walk sign is on. At the same time, a car is moving on the road because the traffic signal is green due to some fault in the traffic system. Now the cyclist misses the collision with the car. Now from this scenario, can we say that something is wrong with the traffic signal? If we are doing testing, we say no, because nothing bad happened. The car didn't hit the cyclist. But note one thing, the crossing of the road by the cyclist and the movement of the car on the road are causally independent. They are not dependent by any causal event. So what we can try to do, we can reorder these two events and make them happen in such a way so that the car actually hits the cyclist. So from a successful scenario, we can predict another scenario where something bad happens. So this is the key idea behind predictive analysis. So what we do, we take the event trace or the execution of the concurrent program, annotate it with vector clock, the dynamic vector clock, the algorithm that I described before, and partial state update which is relevant for the formula. And we construct something called computational lattice, which you can find actually in the literature of distributed systems. Now, one of the property of this computational lattice is any path in this lattice is an execution which is equivalent to the original execution. So what we have to do to check the formal specification against all the executions, we have to enumerate all the paths in this lattice and check them against the formal specification. And for this we will just consider pastime linear temporal logic formula. And if we implement this naive thing where we enumerate all the execution paths in this lattice and then check them against the formal specification, then the time complexity would be linear in the size of the formula and exponential in the size of the lattice, because the number of paths in this lattice is exponential. We proposed a new algorithm based on dynamic programming, which constructs this lattice on the fly and takes the cross product with the formula. And there we showed that it can be done in time, which is linear in the size of the formula and linear in the size of the lattice. And finally, we proved this theorem, which shows that if we are given some temporal logic formula, and if we can find a violation of the formula against during running this algorithm, then there exists at least one linear order which actually violates the specification. So our original execution may not violate the property, but from this algorithm we can find bugs in other closely related executions of the program. So as a result, we got a combination of three methods. Yes?
W here is the number of states, the lattice?
W is the width of the lattice.
Width of the lattice.
What?
Wait, so what is the width of the lattice?
This thing, the maximum distance from one end to the other end, or the actually it's equal to the number of nodes in a particular level of the lattice. That's how we define the width of the lattice. And the L is the length of any path in this lattice.
How by the length of the event trace?
Yes. So that's a good point. Actually, it may happen that the program has very unsynchronized events. And in that case, the size of W can be exponential in the size of the trace. But that happens very rarely. And in that case, we propose something which we call a causality cone sweeping of the lattice, where we show that not all the nodes in the lattice are relevant. Because you may not want to permute two events which are like happening 1 day apart. You do not want to. And if you want to do that, they will fall far in the lattice, and we don't want to explore them. So we have some mechanism to avoid that explosion. Yes.
So the reason why you can get linear in the size of the formula is because you only examine a finite set of states.
Yes.
Because if you do runtime analysis,
yes,
it would be
yes,
exponential.
Yes. Here we are only interested in safety properties. We cannot verify a liveness property or something like that.
Well, but it's static as well. It's not you're not dynamically checking for conformance against a given formula.
Yeah, it's static in that sense. And the linear complexity only occurs in case we have a past time linear temporal logic formula. In case of future time, it actually becomes exponential in the size of the formula. But the formulas are always small, so it doesn't pose a problem. Okay. So we have a combination of these three methods, which is concolic testing, race detection and race flipping, and predictive analysis, which gives us an automated and an effective approach for testing concurrent programs, not only to find generic problems in the program, but also to find bugs related to the formal specification. Now, we implemented these methods in two tools. Excuse me. One is called the jCUTE, which is for testing C programs, and other is called jCUTE, which is for testing Java programs, and both the tools are available online for download. We did some case studies. We tested several data structure libraries in C, and one such library is the sglib library, which is a popular C library for data structures, and it has been widely used, and it's used in one of the commercial tools called X-Refactory for refactoring C and C++ programs. So we took this library and tried to evaluate our tool, how it works. But surprisingly, we discovered two bugs in this library. And one is the segmentation fault, which occurs when a doubly linked list, non-zero length doubly linked list, is concatenated with a zero length list. And the other is a bug in the hash table, which is an infinite loop, which occurs in this isMember function of the hash table. And we reported these bugs to the developers, and they acknowledged and they fixed it in the next release. So here is the statistics for this case study. you'll see that in most of the cases the runtime of testing is less than 5 minutes. We restricted our depth to 50 and we got a coverage which is, okay, something is wrong. It's on all the time. The coverage we got is almost around 96% or more. In case of hash table, since it uses some complex hash function which is not friendly to the symbolic execution, we got a coverage which is like 85%. And in case of red-black tree, it had lot of branches and everything, so we got a runtime which is pretty bad, which is like 45 minutes. And we also got a coverage like 70%. This is low because they introduced a lot of assertions just to check whether the correctness of this hash table, and these assertions cannot be violated anyway. So we got very good low coverage. Here the coverage is with respect to the branch coverage. We also took the, yes. Yeah, so we only consider 50 branches in a given path. 50 branches which are symbolic. So it may also, we just ignore the branches which are non-symbolic. So
do you try by increasing the bound and see what happens?
Yeah, then we don't get, we do not get to explore the whole computation tree in reasonable amount of time. It blows up. Because whenever you go down, you get exponential blow up, and it can.
From these numbers, an idea what's the relation of timing spent in the concrete part of Concolic and the symbolic part. So how much does the constraint solving infrastructure cost you?
That's a good question. Actually, I didn't make any study of that. But since we do many approximations, we only maintain like linear constraints and pointer constraints which are equality and disequality. Our symbolic execution is very fast. And constraint solving just uses LP solve. And it is also quite fast. So it doesn't take that much of time. But it's always going to be several orders higher than the concrete execution. Because for everything, every operation, you have to call a symbolic function which does the manipulation. Yes?
So usually what would happen is that if there are 2 or 3 unrelated branches, then you'll get you'll get an exponential behavior.
Yes,
which
that's true.
So did it happen do you think it's happening in practice?
Actually, the number of branches that actually depend on the inputs are quite low. So we managed to explore the tree in most of the cases. And we found that in most of the cases they are correlated. They are related by the inputs, the branch, the symbolic constraints. And it doesn't happen that they are not correlated. So that's my experience. But it may be the case where they are totally unrelated and you end up exploring more than what is required.
If they are related, then I'm surprised that you are seeing a blow up after 50.
It was not up to 50. It blew up when we went to like 100 or something. We did some binary increment. So I would not say like 60 or something. And there are several reasons behind that. I can take this offline. So another library that we tested is the JDK 1.4 java.util library, which implements several thread-safe collections or data structures. And the claim is that if you execute several methods of a data structure by several threads, then they can be serialized as if they are executed by a single thread. And we took this library because we thought this is a good case study to evaluate our tool. But surprisingly, we discovered previously undocumented concurrency-related bugs in this library, such as data race, infinite loop, uncaught exceptions, and deadlocks. And one such example is this one, this linked list. If we execute this clear and contains all by different threads, we actually can get into an interleaving which actually leads to an infinite loop.
For this example, you have to instrument. So what is the function that you're testing?
Well, that's a good question. So for this kind of testing data structure libraries, we actually wrote a test driver, which in a loop calls the functions non-deterministically. Different functions of a given library non-deterministically and by different threads. And that's how we perform the testing.
And these test drivers are parameterized by input.
Yes. So the linked list can be an input, something like that. And here is the detailed statistics. I don't know, it is behaving. I'll use this. So here is the statistics, which shows that we actually got a number of errors related to data race deadlock. But at a point that these are only due to a couple of problematic design patterns used in the implementation of this library, and they can be fixed easily. We also compared our tool with two other tools which are state-of-art model checking tools. One is the VeriSoft tool for model checking C programs, and there we took the implementation of a Needham-Schroeder protocol and a TMN protocol, and it took less than 15 seconds to find a known attack in these protocols. In comparison, VeriSoft took 8 hours to find the same bug. When they used a combination of heuristic search and manual guidance, they found the bug or the assertion violation in 55 minutes.
So
Yes.
in the previous slide, the number of threads were 5.
Yes.
So why 5? I mean, did you find a lot of bugs that you couldn't find with 2 threads, or is there any particular reason for 5?
Well, you just pick 5 threads. There is no... Because 2 threads may not show up bugs, that's what we thought. But in most of the cases, actually, we found that you can actually find the bugs with 2 threads in these things. Yes.
So how is the attack specified in the next?
Yes. So this implementer of this Needham-Schroeder protocol actually implemented the adversary model and put some assertions which, if violated, indicates that there is an attack in the program. So we didn't look into the code. We just took it for granted and we tested it.
Just a manipulated program.
Yes, yes. So the other case studies, we also compared with the case studies made by the Java Pathfinder tool from NASA Ames. And one of the case studies is the DOS real-time operating system. And there we found a subtle time partitioning error in less than a minute. In comparison, Java Pathfinder actually ran out of memory when they tried to model check the actual program. So they had to perform some abstraction, and then they took 11 minutes to find the same problem. Since jCUTE, which is the testing tool for C programs, is implemented in C itself, we thought we should test the tool by using the tool itself. And so we took several data structure libraries used by this tool and tested using jCUTE. And I was quite confident that there will be no problem in the program because I'm quite good programmer, so. But unfortunately, I discovered some segmentation faults and memory leaks in the program. And after that, I've been programming very carefully, and I always check jCUTE with jCUTE before checking in the program. So these tools are made publicly available in December or January of this year. And it can handle whole of C and Java programs. And the binaries are available for download. And researchers and developers actually download this tool and they're using in their research or in development work. There is some commercial interest also. We filed 2 patents on this technology, and a testing company is interested in licensing the IP. Illinois Ventures is also interested in starting a company out of this. But my personal interest is to do some research impact on software reliability. So that ends the technical part of my talk. And now I'll give you a brief overview about the big picture and my research in other areas. So I focused on this domain, which is dynamic program analysis and testing. So I described today concolic testing and rest flipping and predictive monitoring, but sometimes testing cannot find all kinds of bugs in the program because of this incompleteness. So there one can use runtime monitoring, one of the methods that I developed. So there the idea is from the formal specification, you synthesize some kind of monitors or state machine, and then you instrument those things inside the program, and then whenever you run the program, they can dynamically check the formal specification against the execution and report any problem in the program. Now, monitoring becomes interesting when you have distributed systems, and there we showed that it can be done effectively by implementing some decentralized techniques. So this is also interesting. I cannot go into the details. So these things are directly applicable to programs, but I also worked on modeling and model checking problems. In particular, I extended rewrite theories with probabilities and called probabilistic rewrite theories. And it's very suitable for specifying or programming network protocols where we replace the non-determinism by probabilities or sensor networks. And for those kind of specification, we also develop statistical model checking where we check a probabilistic property like quality of service property, etc. against the formal specification. In a collaborative work, I also applied computational machine learning to verify the safety properties of infinite state systems. And there the idea is the reachable state space of infinite state system is often regular. So you can use machine learning techniques to learn this state space and check it against the formal specification. I'm quite excited about this work. And there are some common themes in my research. They are all dynamic. I saw a lot of interaction between these various ideas. They're scalable, they're automated, and I do approximations from time to time to get rid of the scalability, to make it scalable. And I brought in ideas from other domains like machine learning, statistics, randomized algorithms, probability theory, operations research, and so on. And I also like to develop tools based on these ideas, and I developed several tools for each of these methods, like Dart, jCUTE, and jCUTE for concolic testing, jMPEGs for predictive analysis, and so on. And we applied it to several case studies. I described some of them. Some other interesting case studies, we found bug in the Mars rover software at NASA Ames using the Eagle tool for runtime monitoring. We also found safety and security vulnerabilities in the open source OC protocol at Bell Labs. We also detected intrusion in the DARPA logs and so on. So software is everywhere. Now I'll give you some future research directions. It is pervading every aspect of our life, and software reliability is a big challenge nowadays. And in my research, I tried to develop methods which not only have rigorous theoretical basis, but also practical and applicable to real-world programs. But I believe we have only scratched the surface of this problem, and there is a lot of things that needs to be done. In long term, I would like to extend these testing methods and dynamic program analysis methods to other domains like hardware testing, testing embedded systems or event-based systems, and so on. I'd also like to develop methods in which the software becomes self-healing. They can monitor itself at runtime and take necessary actions so that nothing bad happens in the system. And my work in runtime monitoring shows some direction in that problem. I'd also like to develop some methods which can give some measurable confidence in the software reliability, some quantitative notion about how correct our program is. And my work in statistical model checking shows some directions in that. And in the near future, I would like to develop methods that can combine static analysis with dynamic program analysis so that we can prune the search space a lot. We can prove correctness of some part of the programs while doing dynamic program analysis and so on. I would also like to extend these testing methods to evolving software where you have different versions of the software. So we have tested some part, now we don't want to redo the whole work for the new version. So how we can do such things using a dynamic program analysis. I would also like to apply it to sensor network, verifying such things, and develop methods where we can verify concurrent programs. And in the process, I would like to combine techniques from other areas like machine learning, randomized algorithms, operations research, and so on. So there are several related work in this whole domain of program analysis, like scalable testing, testing concurrent programs, specification-based testing, software model checking, static analysis, type system and safe programming languages, runtime monitoring, and rest detection. This is not an exhaustive list. And in my research, I actually collaborated with several researchers, both from academia and industry, and I'd like to thank them. And finally, here is my conclusion. Thank you.